Welcome to the 10th and next to last preview video for Math S-322. The topic for today is Darboux and Riemann integrals. Last year my students tried to talk me out of including this topic in the course, and I finally decided that no, we had to have a definition of the integral that was something different from the antiderivative. It's unfortunate that most students who've taken a first course in calculus think of an integral as meaning an antiderivative, but we really need to define an integral in a way that has nothing whatever to do with differentiable calculus. This was initially done in the early 19th century by Riemann, and Riemann sums have made their way into most calculus courses. The idea was improved in the late 19th century by Darboux, and I was a bit surprised to discover Darboux integrals in Ross's textbook, but the more I think about them, the more I like them. And they are a very nice example of using the completeness axiom of the real numbers to define a quantity as either the greatest lower bound or the least upper bound of some bounded set. This is tricky but not incomprehensible. Let's get started. We've got a function defined on a closed interval from a to b, and we're going to insist that it's bounded on that interval. It doesn't have to be continuous. It can actually be quite badly behaved as long as it's bounded. Now for some definitions of notation. Let's consider a subinterval of this closed interval. Let's think about the largest value achieved by the function on that subinterval. The function is bounded, so this supremum necessarily exists, and I'm going to denote it by capital M of f and s. This is the supremum of the function f on the subinterval capital S. And similarly, I'll write the infimum of the function on that same subset as little m of function f on subset S. Finally, I have to define a partition of this interval from a to b. To form a partition, we're going to have to come up with some points of subdivision. The first one, which I'll call T0, agrees with A. The last one, that I call Tn, agrees with B. And then T1 is bigger than T0, T2 is bigger than T1, and so on. The way Riemann integrals are traditionally done in a first course in calculus is we space these out evenly. So if a is 0 and b is 1, we might have t0 equals 0, t1 equals 0.1, t2 equals 0.2, and so on. But here, as long as these are increasing, and there are n of them, the partition is completely arbitrary. Now I can define the upper Darboux sum of the function f with respect to the partition P. Here's how I'm going to do it. I'll start with the first subdivision, the subdivision that goes from T0 to T1. I'll take the length of that subdivision and multiply it by the supremum of f on that subdivision. I'll then do the same for k equals 2 with the subinterval from T1 to T2. And when I sum all these quantities up, I get something that's a pretty good approximation to the integral, and it in fact is guaranteed to be larger than the value of the integral. This is what I mean by the upper Darboux sum. Take an arbitrary partition, and in each subinterval in the partition, use the largest value achieved by the function. Well, you can guess how the lower Darboux sum is going to be defined. Exactly the same, except we use the infimum rather than the supremum. And since an infimum can never be larger than a supremum, we conclude that for any partition, the lower Darboux sum is less than or equal to the upper Darboux sum. Furthermore, the lower Darboux sum is going to be greater than or equal to what I would get if I used a partition consisting of just a single subdivision and took the infimum of the function on the entire interval from b minus a. And the upper Darboux sum is less than or equal to what I'd get if I took the length of the entire interval and multiplied it by the supremum. Now I can define Darboux integrals. For any partition, we have a Darboux sum. There are lots and lots and lots of partitions, but these give us a set of real numbers, and furthermore, those real numbers are bounded from above. Let me remind you why. There's the bound. So I'm going to define the upper Darboux integral as the least I told you this was hard. I had to stop and think there, but now I've recovered my explanation. When you make a finer partition, you're going to make the upper Darboux sum smaller. And so we have this set of upper Darboux sums, and there's some number which is the largest real number that's less than or equal to all of these, the infimum. That's what I'm going to mean by the upper Darboux integral. To define the lower Darboux integral, I will note that as I use finer and finer partitions, the lower Darboux sums get larger and larger, and this set of numbers has a least upper bound. I'll call that L of f and state that that is the lower Darboux integral. These quantities always exist because a non-empty bounded set of real numbers always has an infimum and a supremum. And so, since the lower Darboux integral is less than or equal to the upper Darboux integral, we can finally define the integral of f. If these quantities happen to equal one another, which is in fact usually the case, then we say that f is integrable on the closed interval from a to b, and the common value of these two Darboux integrals is the integral of the function. So we have successfully defined the integral of a function in a way that never mentions differential calculus. Now, how can we make finer and finer partitions? Well, let's think about two partitions P and Q with the property that the subdivision points in P are a subset of the subdivision points in Q. In other words, you make Q by taking the partition P and further subdividing one or more of the subintervals. So Q is a finer partition than P. This is hard to remember. You say P is a subset of Q, but that means that P includes fewer subdivision points. It's a coarser partition. Q is the finer one. In that case, we're going to be able to prove the following. Clearly, for the finer subdivision, the lower Darboux sum is less than or equal to the upper Darboux sum. And we can also prove that for a finer subdivision, we get a larger lower sum, and for a finer subdivision, we get a smaller upper sum. If you try doing this in the standard elementary way by using a subdivision into n equally spaced subintervals, you discover that with 7 subdivisions, you don't get a partition that is a refinement of what you'd have with, say, 6 subdivisions, because the subdivision points don't agree with one another. That's why this general partition is the key to proving these results in general. Okay, now we're in business. Once we've proved this, we say, now we'll pass from Darboux sums to Darboux integrals, take the infimum and supremum over all partitions, and we can conclude that the lower Darboux integral can never be larger than the upper Darboux integral. How can we test for Darboux integrability? Well, that in fact turns out to be fairly easy. Pick a positive epsilon. If for any positive epsilon you can find a partition with the property that the upper Darboux sum exceeds the lower Darboux sum by less than epsilon, then the function is integrable. What would happen if f is unbounded? Well, if f is unbounded, if it's unbounded above, the upper Darboux integral will no longer exist. If it's unbounded below, the lower Darboux integral will no longer exist. So this definition only works for bounded functions. What about Riemann integrals? Well, a Riemann integral is very similar to a Darboux integral. Again, we use a partition, except for the Riemann integral, instead of choosing the supremum or the infimum, we choose some arbitrary point in the subinterval. And there's no specific rule by which we choose the point in the subinterval at which we do the evaluation. We can choose it at the left endpoint, t sub k minus 1, and get a left Riemann sum, or we can choose it at the right endpoint and get a right Riemann sum, or we could choose it in the middle and get a midpoint Riemann sum. These Riemann sums are familiar to most students who have studied calculus. Now we can say that a function is Riemann integrable, and the value of that Riemann integral is little r, if there exists such a little r with the following property. I challenge you with some positive epsilon. You come back and respond to my challenge with a positive quantity delta that has the following property. If we take any partition for which the so-called mesh, the length of the longest subinterval, is less than delta, then the Riemann sum for that partition differs from the quantity r in absolute value by less than epsilon. So the difference between a Darboux sum and a Riemann sum is, for the Darboux sums, you always use either the largest value or the smallest value, the supremum or the infimum. For a Riemann sum, you can have a more general rule for choosing the representative value of the function. And ultimately, it doesn't make any difference, because you could prove that a bounded function is Riemann integrable if and only if it's Darboux integral, and if it is, the values of the two integrals agree. Now that we've defined integrals, we can prove a lot of properties that are well known. I'm assuming we've got two functions that are integrable on the closed interval from a to b. Let's let c be some arbitrary real number. First property, multiply the function by c, you multiply its integral by c. Take the sum of two integrable functions. The integral of that sum is the sum of the integrals. If function f is never larger than function g on the integral of f is less than or equal to the integral of g. If g is never negative and it's continuous and its integral is 0, then the function g must be the zero function. This, you will discover, is not true if you remove the requirement that the function be continuous. If a function f is integrable in the sense of the Darboux integral, then so is its absolute value, and furthermore, the absolute value of the integral is less than or equal to the integral of the absolute value. Next, suppose we've got a function defined on the interval from a to b, and we pick some point c in between a and b. If f is integrable between a and c, and also integral between c and b, then it's also integrable from a to b, and as everyone knows, the integral from a to b is the sum of the integral from a to c and the integral from c to b. All these properties are provable from our definition of the Darboux integral. And finally, very useful result, if a function is piecewise monotonic, that is, if on a to b we can find a finite number of subdivision points so that on each subdivision the function is either increasing or decreasing, or if the function's piecewise continuous. If it's continuous on the first subinterval, then may jump, and it's continuous on the second subinterval, and so on. Either piecewise monotonic or piecewise continuous is enough to prove that the function is integrable. This is tricky stuff, and there are a lot of details we'll need to go into in class, but I think you'll come out of this with a complete understanding of how the integral of a function is defined, and then we'll be set for our final class to state and prove the fundamental theorem of calculus, which connects derivatives and integrals.